Maybe you can put this to smaller, or yeah, that's also.
There were people asking, people already asking for it.
All right, I mean. So wait, how does the clicker?
Yeah.
Listen to. It's making a sound.
Yeah, maybe if I click on here. Can you try it now?
Oh,
okay, yeah, I think it was just not clicked on this. Okay, hi everyone. So we are about to start today's seminar, and it's a pleasure for me to introduce Noah Miller, who just started as a postdoc here, who's going to today talk about cellular gravity and maximal helicity violating amplitudes. Take it away, Noah.
Okay, thank you. Thanks for coming. I might also talk, time permitting, I might also talk a bit about maybe how it should be self-dual gravity, MHV amplitudes, and also LW 1 plus infinity symmetry, although we'll see if we have time, but okay. So as a bit of background, in pure Einstein gravity, the scattering amplitude for an arbitrary number of positive helicity gravitons to scatter is 0 at tree level. So a bunch of plus gravitons. This has no amplitude at tree level. But if you make a single positive helicity graviton negative, the amplitude is still 0 at tree level. But if you have two negative helicity gravitons and an arbitrary number of positive helicity gravitons, the amplitude is finally not 0. And this is called the MHV amplitude, maximal helicity violating amplitude. And it's the simplest non-vanishing amplitude just in pure Einstein gravity, you could say. So some of you might be familiar with the gluon MHV amplitude, which is sometimes discussed in QFT courses. So if you have an arbitrary number of positive helicity gluons, just in pure Yang-Mills, let's say, and let's label the two negative helicity gluons by I and J, which let's just say are I is n+1 and J is n+2, then well, we can always write a Yang-Mills amplitude in this colored ordered format where here the SUN or SU whatever, SU3 or whatever, you have generators for the algebra in some sort of cyclic ordering, and here we have the color stripped amplitude. And it turns out that there's this very simple formula for this amplitude, which is the so-called Park-Taylor formula. So here I've written it. So here I've written it with the two negative helicity gluons here and here in the color ordering. And so we have ij to the fourth on the top. Oh, if you don't know what these angle and square brackets are, don't worry too much about that. But I just want to show you it's this nice simple formula. Then we have some cyclic ordering in the bottom. And this formula is really not clear how where it comes from just from Feynman diagrams. If you want to compute these amplitudes to take 5 or 6 point or whatever, it'll take many hundreds of Feynman diagrams and it'll miraculously simplify to this formula. And this formula is sort of like maybe one of the mascot formulas of the modern study of scattering amplitudes, just for its simplicity. But okay, why should anyone care about MHV amplitudes? Aside from the fact that they correspond to real physical processes, which you could see, for instance, in like the high energy scattering of like hadrons and stuff like this. But from a more mathematical standpoint, one reason many people are interested in these amplitudes is you can build any arbitrary tree level Yang-Mills amplitude out of them. So this is the so-called MHV vertex formalism. So this is extremely non-trivial. But if you just have some arbitrary Yang-Mills amplitude with any pluses or minuses on the outside, each vertex can be an MHV amplitude of its own with an arbitrary number of positive helicity gluons coming off of it. and they're connected by a propagator which switches plus to minus. And so these are really just Feynman diagrams where each vertex is the Park-Taylor formula. And I mean, and it's more efficient than, Feynman diagrams, by a lot. So I think many people would say this is, as good as you're going to get for tree-level Yang-Mills. You could say that this sort of formalism solves tree-level Yang-Mills as well as you're going to do. And it can get a lot of loop-level stuff too, but, whatever. But yeah, it's not known if a construction like this can be made for gravity, and that's something there are many people still wondering. But okay, so where does the simplicity of the Park-Taylor formula come from? It's really not clear at the level of Feynman diagrams where it comes from. And one sort of reason that it's so simple is because there exists this sort of special sub-theory in Yang-Mills called self-dual Yang-Mills. So if F is the curvature 2 form, just classically, let's say, you could take the Hodge star of a 2 form, and if the Hodge star of F is equal to IF, that's a self-dual, you call it, that'd be like a self-dual connection curvature. And so any solution to this equation, the self-dual Yang-Mill equation, will instantly satisfy the Yang-Mills equation of motion. So if you just have, the infinite space of solutions to the Yang-Mills equations of motion, there's this special, slice, the self-dual Yang-Mills. And this is a very, this theory has a lot of symmetries mathematically. It's an integrable system, self-dual Yang-Mills, and sort of the simplicity of the integrability of self-dual Yang-Mills sort of gives the Park-Taylor formula. But in this talk, we won't be interested in self-dual Yang-Mills. We're interested in self-dual gravity. So, okay, what is the definition of self-dual gravity? Very simply, it's just any space-time which solves this equation. So it's, if you think of the Riemann tensor as a 2 form, if that 2 form is self-dual with respect to the Hodge star, then you call this a self-dual space-time. And by messing around with some with some index tricks, you can show that any space-time which is self-dual automatically satisfies the vacuum Einstein equation. So this is like a subset. Self-dual solutions are a subset of vacuum Einstein, except for the flat metric. None of these metrics are going to be real in 1,3 signature. So if we have the Minkowski metric and add like a little perturbation to it, that perturbation will have to be complex. So in 1,3 signature, these self-dual spacetimes will be complex. They have complex metric perturbations. Oh, yeah, and you should really think of these spacetimes as containing only positive helicity gravitons. So it's sort of like Einstein gravity. If you took out all the negative helicity gravitons, that will give you self-dual gravity. So self-dual gravity is the main object of study of a branch of mathematical physics called twistor theory, which I won't get into here. I just wanted to mention twistor theory. Here are some beautiful hand-drawn images from Penrose's original paper. Basically, there's a way that you can describe these self-dual spacetimes in like a very mathematically rich, and you can sort of solve self-dual gravity with twistor theory, but we're not really going to discuss this. Okay, here's a more pedestrian formulation of self-dual gravity in a way that you can actually work with it. So for every self-dual metric, there always exists some coordinate system. Now here I'll use the coordinates u, u bar, w, and w bar, where we can write the metric in this following way. So we can parameterize the metric with the following scalar degree of freedom. Where here the scalar field is phi, and this scalar field satisfies an equation of motion called Plebanski's second heavenly equation. So there's Plebanski's second heavenly equation. So here, box is just the normal flat space wave operator. And this Poisson bracket here is the Poisson bracket in 2 of the space-time variables, u and w. So the Poisson bracket doesn't include u bar and w bar, just u and w. So Plebanski's second heavenly equation, it's basically, wave equation with this very strange interaction term that, well, it manifestly breaks Lorentz symmetry, although at the end of the day, you can always get it back. But it's a very simple equation, which makes it nice to work with.
So your phi here is your method field?
Yeah, it's the graviton. This field is really corresponds to a positive helicity graviton field. There's just a single scalar degree of freedom because we only have just positive helicity gravitons. So in 1,3 signature, we can take U bar, W, and W bar to be these light cone coordinates. So here, U and U bar in 1,3 signature are both real independent coordinates. And it's just this, it's the standard light cone coordinates, time minus Z, and here we have U bar is time plus Z, and then W and W bar are X plus IY and X minus IY. So this is sort of a funny metric. So a fact about self-dual spacetimes is that they're all Kähler manifolds, actually hyperkähler. So, Kähler manifolds are parameterized by a Kähler scalar, and you can think of this this scalar phi as sort of being a close cousin of the Kähler scalar, a little different. Now, this is a strange sort of parameterization of metric, but I'll just say that it's actually really not so strange because you can show quite simply that this metric is actually in sort of a nonlinear transverse traceless gauge. So if H is the metric perturbation to flat space, it's traceless, and it's also transverse with respect to. So here we're really just, so this is really a convenient parameterization for discussing scattering. Okay, so one exact solution to Polbansky's second heavenly equation is just when phi is a plane wave. So this is actually an exact solution to this equation. Both box will annihilate it, and this thing will also annihilate it. So if you plug this plane wave into the metric, you'll see that what you have is a finite sized right-handed gravitational wave for some specific choice of the polarization.
Sorry, I'm confused. How can the one single scalar degree of freedom match with the degree of freedom of the traceless symmetric?
So normal gravity, after all the gauge fixing, you can think of it as just having two scalar degrees, 2 degrees of freedom for right-handed gravitons and left-handed gravitons. And here we've got rid of all the left-handed gravitons. So this is a very specific choice of, we're fixed a lot of residual gauges and so forth to get this exact metric. There's no extra freedom here.
Sorry, so any subgroup of metric is.
Yeah, there's always some coordinate system which you can locally write any self-dual metric like this. It's sort of like it's a Kähler manifold, so that's like another way you could write it, Kähler scalar.
This is local, the global and phi would be.
I don't know if I have any particular results to tell you about globally. But locally, okay, but because the equation of motion is nonlinear, stuff interacts. If you were to sum 2 plane waves, that wouldn't be an exact solution. And this motivates the definition of what's called a perturbator expansion, which sounds like which is sort of a crazy term, but for a pretty straightforward concept. So a perturbator expansion is just, so if this is something which you can have a perturbator expansion for any equation of motion, not just the specific one we have here, but it's just any solution which has a sum of plane waves as sort of the linear part of the solution. So here, these epsilon i's, where I goes from 1 to n, these are infinitesimal parameters, where like any individual epsilon I squares to 0, but the product of distinct epsilon i's won't be 0. So they're like these tiny, they're like little amplitudes for the waves. And if you start with a solution, you say, okay, I want to have a sum of plane waves where each plane wave has this epsilon i's amplitude, and I want to recursively solve the equation of motion of higher and higher orders in epsilon. This is called a perturbator expansion. And the perturbator expansion also will terminate at a highest order term with an order of epsilon1 all the way through epsilon n. So it stops once you have a term with all the epsilons in it. Now one usually solves for perturbator expansions using Feynman diagrams. So this equation of motion it has an interaction term which we could, solve for using this Feynman diagrams with a particular vertex, although we won't be using them in this talk. So in order to set up how we can, what the solution is, the perturbation expansion, we'll start by parameterizing momenta, the sort of energy scale omega, and two stereographic coordinates z and z bar. And we're going to define the plane wave seed functions. So I'll denote phi I just to be a plane wave with an epsilon I thing out front. So these are the seed functions, which we seed the expansion with, and then that determines the rest of the expansion. Right, so the epsilon i's are the analogs of the finite amplitudes AI. And right, so for the simplest possible, let's say, expansion, which is 2 gravitons, what does the expansion turn out to be? Well, one can show, it's not that difficult to show, that the expansion turns out to be the following. So we start with our 2 seed functions. This is just one graviton with a momentum P1, another graviton with a momentum P2, and then the final term of the perturbation expansion turns out to be the following thing. So 1 over Z1 minus Z2, and then the Poisson bracket of the 2 seed functions. So now I'm going to use sort of, just say sort of like a guess, which will turn out to be true. So, well, okay, how can we then solve for the next order? So if we have 3 seed functions here, well, we're going to have these terms in the perturbation expansion as well. But then the more interesting thing is, what's the final term with the epsilon 1 times epsilon 2 times epsilon 3, right? See, these only have 1 epsilon in them, these have 2 epsilons in them, and the final term will have all 3 epsilons in it. So let's make a guess, okay? Let's just take the 2 graviton term, 1 over Z1, 2, and then the Poisson bracket 1 and 2, and just kind of place, just kind of take the 3rd seed function and then kind of put this same combination in here with the 1, and then put it and then add that in there with 2. So this is sort of an inspired choice of, guess for how it's going to go in the future. So we just sort of maybe we recursively guess that we can keep putting it in here. And this, I'll just say it kind of has the character of sort of an operator product expansion in a conformal field theory, although I'd like that to be more precise. And then you could do that again to get the 4th order term and so on. So you just recursively take the previous thing and you just place this sort of combination with all the seed function, you keep getting more and more. And this turns out to solve the perturbator expansion. And these terms are, you can write them with binary tree graphs, where you sort of take the previous graph and you just kind of keep sticking in the next one into all the other previous things on the next graph. And these perturbator expansions don't appear to be permutation symmetric, right? Like here, we're not treating 1, 2, and 3 all the same way, because we took 3 and stuck it into 1 and 2. So, you would think that the expansion should be permutation symmetric. Let's take things a step further. So we can define a differential operator, which is just the normal derivative, partial mu, but we'll define partial mu I to be the derivative. It's a symbol that only acts on the ith seed function. So if we act partial mu I on phi I, we just get the derivative acting on phi I. And then if we have partial mu I acting on phi j, that's just 0. I'm just saying how the symbol works. So we can furthermore define this other symbol dij to be a Poisson bracket that really only acts on the I and j seed functions if you act it on a string of seed functions. So if you then take this expansion, let's just say for the 3rd order thing, and you use the product rule and you use these symbols to write out the product rule for every individual term, what you find is that in the end, at the final line, you actually do have something that's permutation symmetric. So the perturbator expansion is actually symmetric in all the gravitons. So in order to discuss this more generally, let's define this graphical element where we have 2 nodes I and j, and these nodes correspond to the seed functions phi I and phi j, just the ith graviton, the jth graviton. And if we draw a line between them, that's just acting with dij over zij, where zij is zi minus zj. Anyone's not familiar with that notation. So you know, dij is just basically the Poisson bracket acting on these two things. So, right, so for n equals 3, if we rewrite it using this notation, we can also express it as a sum over these diagrams. So here, the three original seed functions, 1, 2, and 3, those are just these simple diagrams, just phi 1, phi 2, phi 3. And then all the second order terms, you know, phi 1, 2, phi 1, 3 are right there. And then the third order terms are all these things. So now I'm going to say how to express the most general thing with n seed functions. So let mathcal Tn denote the set of all marked connected tree graphs with n or fewer nodes. Each node has a distinct label contained in 1 through n. So examples of graphs, let's say in T9, where n equals 9, are these things. So this is just, let's say, a seed function. Here's another graph that could be in T9. Here's a bigger graph that could be in T9. So it's all the connected tree graphs. So as an example, so if we have a single graph here, or here let's see, here's 1 connected to 2, 3, 4 is connected to 5. This would correspond to this following term. So here we have a d12 over z12 that connects 1 and 2 here, and then d13 over z13, and you know, there's 4 edges there, so there's 4 these operators, and there's 5 seed functions. There's 5 seed functions, so we can just create a sort of graphical dictionary. And the general formula for the perturbator expansion is given as follows. So here we have the perturbator expansion, which is a function of n seed functions. So seed functions 1 through n, these are just n different gravitons. And I'm saying the full perturbator expansion is just a sum over all these tree graphs, where each tree graph, you know, for each edge, you have a dij over zij, then you multiply by all the nodes in the graph. And so there's a full perturbator expansion for self-to gravity, yes.
How many terms appear in the sun for an
Uh,
event?
I think I have it in there's some formula in the paper. Something like
The factorial?
yeah, it's roughly something like that. N to some n minus 2, something like that. Yeah. There's some, it's from some theorem due to Euler or Cayley or something. It's some old formula. And I'll just say that if you play out the similar story in self-dual Yang-Mills, you don't, if you want to solve for perturbator expansion self-dual Yang-Mills, you have a sum over color orderings. And I'm just sort of saying that these trees are these are the analogs of color orderings in Yang-Mills. Okay, so here's the only way I know how to prove this formula. So you really shouldn't give proofs and talks, but well, I feel like it gives a flavor for how this all works. So I'm just gonna do it, and then it'll be over. And you know, the main thing is to give you a flavor for how one can manipulate these tree formulas. So the proof works by just verifying that if we plug our tree formula into the second heavenly equation, we have to solve the second heavenly equation. So, okay, so this box here is just this wave operator. Here we have the Poisson bracket again. And explicitly, p dot x in these light cone coordinates is given by this following combination. So if you have a seed function phi I, you know, epsilon I e to the I p dot x, we can verify this very simply that if you, let's say, differentiate with respect to u bar on phi I, you get negative zi times the derivative with respect to w. And if you differentiate respect to w bar, you get negative zi times the derivative with respect to u. And another sort of short 2-line computation shows that if you act with box on a product of 2 seed functions, you get z, in using this thing here, you get zij times dij acting on these seed functions. So just you'll have to take my word that the short two-line computation really gives this to you. And using these combinations, it's natural to find some more graphical elements. So here we have the straight line, which is dij over zij that we saw before. Then we can also define the Poisson bracket acting on two of these seed functions with a wiggly line with an arrow. And you need the arrow because because there's an orientation to this edge, right? Because if you switch I and j, you get a minus sign, so you need the arrow to show minus sign. If you switch I and j here, there's no minus sign because it's dij over zij, so two minus signs cancel out. And then here the box is zij times dij, and we'll denote this with a double line. That's sort of the box. So if we act with, let's say, the box or the Poisson bracket on products of multiple seed functions, the product rule differentiation will tell us to expand things in the following way. So we act the box on, let's say, a product of three seed functions. You act the box on the first two, then let's say on the last two, and then on the first and the last one. And that will give you box of this. So, okay, so if we went graphically, how do we express the product rule? So the box on phi, here we have to sum over all placements of the double edge between all pairs of nodes in a graph. And we'll denote this set of graphs with this extra double edge placed in as Tn with a box on it. And if we have this combination here with a Poisson bracket and then an extra u and w in it from the second half of the equation, because there's also a u and w here, we really have to place two squiggly lines. One squiggly line for the Poisson bracket, another squiggly line for this u and w. So here we have to sum over all placements of two wiggly edges between two distinct graphs, the two graphs coming from the phis in the two slots. And we'll denote these graphs via T and P2. So, okay, so here's an example. So if we want to compute box of our perturbator expansion, we have to sum over all graphs where all the graphs have a double line placed between two of the nodes. And then if we want to have the other thing with the Poisson bracket with the u partial w, we have to have two graphs, but there have to be two wiggly lines going from one graph to the other graph. And now I've sort of drawn these two graphs in a suggestive way because you can see that you can kind of actually create sort of not quite a bijection because there'll be multiple graphs, but a relation where these graphs look the same and they all have a single cycle in them, right? This has one cycle and this has one cycle. It actually looks, like a chemical or something, but yeah, these graphs both contain a single cycle. Okay, good. And now, crucially, notice that this double line graph has a zij here, but the single line graph has a 1 over zij. So to convert a double line to a single line, you just have to multiply by zij squared. And likewise, if you want to convert a squiggly line into a straight line, you just have to multiply by a single zij. Right, so here if we group our graphs such that there's a cycle, okay, then here's a double line here, the double line can be anywhere in the cycle, right? We just multiply by the sum of squares of all of the zij's in the cycle, and that's the sum with the boxes. So we sum over all groups like this. We just have this thing up front, and then similarly for the second set of graphs. Now we have to sum over all placements of the two squiggly lines. And now we have to sum over all distinct pairs of zij's. Right, so here we summed over all these things and we got the graph without any double lines times this. Here we summed over all these, we got the graph without any squiggly lines times this thing. And so we can then finish the proof by showing that, well, we have to show that this factor here equals this factor here, right? And then we'll show that they're the same, but that can just be done by sort of squaring 0. So if you have the sum of all zij's in a cycle, it'll be 0 because here we have a zij. So here we have a zi here and then a minus zi here. So this just sums to 0 and you square it, you get 0, and then you FOIL this out. And on one side, you'll get the sum of squares, on this side you get the product of pairs, and then you're done. So this will work for a cycle of any size. And anyway, that's the proof that this perturbator expansion solves this. Okay, that's the end of that. Okay, but yes.
Which steps of that proof use that each of the infinitesimal squares to 0?
Oh, yeah. So yeah, it's a great question. When you have this thing here, you always, when you have a graph here and another graph here, you never have the same node. If the two graphs share a node, they go to zero. So you always have graphs with distinct nodes in them.
Should we be thinking about these epsilons as operators of some kind or normal?
You should think of them as like a graviton is like a really tiny gravitational wave.
Yeah,
And it's a gravitational wave with a really tiny amplitude. There's the amplitude of the gravitational wave.
but these are really just complex numbers that are just small. How do we justify our
They could-
assumptions on their products?
Okay, I think I'm gonna get back to that very soon, and you'll see something which you'll probably like. Okay. Okay. So I probably want to talk about L infinity. Well, maybe I don't know. Okay, what do these trees have to do with the gravity MHV amplitude, which is how I started this talk? So an all multiplicity form, but when I say all multiplicity, I mean any number of positive helicity gravitons. An all multiplicity closed form expression for the MHV amplitude was written down by Nguyen, Spradlin, Bolovich, and Went, NSVW in 2009. So let's say we scatter n+2 gravitons and the 2 minus gravitons, let's label them by I and J once again. Their formula writes the MHV amplitude as a sum over all trees where the trees of a positive helicity gravitons. So in other words, here they're summing over, well, actually, they should just be trees with the maximum number of nodes. But in any case, so anyway, they're summing over these trees with positive helicity gravitons, and here they have these factors with the spinor helicity formalism. If you don't know what the spinor helicity formalism is, you can just sort of cheat and say that the angle bracket ij is zij, and the square bracket ij is basically the same thing, but with the two energies out front in a particular parameterization. So you can sort of see that this looks very similar to our thing. So I'll just sort of say that the way that this all, I'll just sort of say that the way this all played out was, I was actually interested in, my original motivation was studying LW1 plus infinity symmetries, and I was trying to show how they act on spacetimes, and I was trying to find like a formula for how to do it, and I came back from winter break and I had all these like tree formulas, and I was like, are these anything? So I asked a postdoc, like, are these tree formulas anything? And he said, oh, those tree formulas are in the MHV formula. I was like, oh, okay. So now I have to I was like, oh, now I have to connect them somehow. So that's going to be the rest of the talk. Okay. There's another way to write this formula called Hodge's formula. We write the amplitude as a sort of matrix determinant, and there's a sort of combinatorial theorem that relates this sort of matrix determinant to summing over trees, matrix tree theorem. But yeah, okay, anyway, the point, so amplitude formulae like the NSV formulae, you don't prove these formulae by like summing over Feynman diagrams and showing the Feynman diagrams you organize. That's way too difficult, especially in gravity. It's too difficult in Yang-Mills, and it's way too difficult in gravity by a lot. So instead, here's historically how the NSV formula was proven by NSV and W. So they first sort of guessed it was true because they were smart people, and they were doing some other stuff, and they're like, I think this formula is true, and then you can check it's true using this method called BCFW recursion, where you can sort of take an amplitude and express in terms of lower point amplitude. So if you have an all multiplicity expression, you can check it's true, and it is indeed true. But one might wonder, can you compute this amplitude explicitly? Not sort of guessing it's true and then checking, just using general relativity. And this was accomplished in 2021, the Damo, Mason, and Sharma, using twistor theory, using their nonlinear twistor sigma model, which they used to, compute this amplitude without, BCFW. And in this paper, we write a second proof, and doesn't use BCFW or twistor theory, just uses Blavatsky's second heavenly equation. So, okay, how do these proofs work? At a basic level, both of these proofs work by computing an on-shell gravitational action for a self-dual spacetime with two anti-self-dual perturbations. So far in this talk, I've told you about how to take how to compute self-dual spacetimes with a perturbator expansion. And if you add two, you can then add two anti-self-dual perturbations corresponding to two negative helicity gravitons. And this is the space-time that corresponds to an MHV process. And so, okay, but if you have the space-time, how do you get the amplitude? So let me remind everyone here about the connection between amplitudes and classical solutions. So here's a scattering amplitude. Let's just for simplicity, just to have as few indices as possible. Let's just say we have some sort of scalar field, maybe phi cubed, whatever. And let's use a convention where incoming momenta have a positive energy and outgoing momenta have a negative energy. And one could imagine a classical solution like this. So here we have a classical solution where we have a sum of plane waves with finite amplitudes AI and a bunch of energies, where here we should really be thinking of ingoing and outgoing have different energies. And in the free theory, you can have coherent states, which are just given by exponentiating the creation and annihilation operators with certain amplitudes. And the sort of, you could say, call it S matrix element of coherent states is given by the coherent state path integral. So in the coherent state path integral, what you naturally find is that the positive frequency data gives you the incoming particles at t is minus infinity, and the outgoing data gives you, the negative frequency data in the future is the outgoing data. And so we're looking for classical solutions with mixed. We're looking at fields with mixed boundary conditions that have certain negative frequency data in the future and a certain positive frequency data in the past. And right, so in the stationary phase approximation, you can just, if you want to evaluate something like this, you would just find the classical solution and evaluate this in the amplitude. Right, sorry. Okay, but let's say, but we're not interested in coherent states, right, with finite amplitudes. We're interested in, actual scattering amplitudes, or just like elementary quanta. But the way you can recover that is just by differentiating with respect to the A1s, A2s, A3s, and so forth. So the tree level, most classical thing is you just differentiate by all the amplitudes. I'm using the word amplitude in two ways, but the A1s through ANs, and evaluate them at 0. And then you can further argue that the connected part of the amplitude, that's just going to be the action itself. So here's sort of the full tree level amplitude, but if you just want the connected part of the amplitude, that's not e to the is, that's just is. And now we can just think about these AIs as being our epsilon i's from earlier. So here we take a solution with these seed functions, and then send the AIs, and then solve for the field, and plug the field into the action, and then that's our amplitude. Okay, so does that sort of answer your question as to where the epsilons come from? So you just kind of differentiate with respect to them, and then evaluating them at 0.
Mhm.
And that's why these things are really quantum. You really think of them as quantum particles like this.
I'm so confused as to why like epsilon1, epsilon2 would give you something non-zero.
Well, because we want to evaluate sort of the maximum term in the end.
Oh, I see.
We're just differentiating with respect to each one once. Exactly.
I see. Okay.
Yeah. So this is right. This is a relationship between on-shell actions and tree level amplitudes. So there's a convenient trick for calculating MHV amplitudes using classical actions. Right. So this can in general be like a very complicated thing to compute, right? In the standard method, you would compute the perturbator expansions using Feynman diagrams, and plugging that into the action can be quite painful. So you want to have you want to use this to your advantage somehow by doing something clever at some step. So here's how you can compute MHV amplitudes with classical actions. So before going to gravity, let's just start with Yang-Mills because it's sort of easier. So the Yang-Mills action is this thing as follows. But you can also add to the Yang-Mills action a topological term that won't affect, won't affect any scattering amplitudes, and you can decompose the field strength into a self-dual and anti-self-dual part. And then if you do that, you'll see that, with this topological term added, the Yang-Mills action can actually be expressed only with the anti-self-dual part of the field strength. So instead, usually you'd write it as, F squared, but you can actually write it as F minus squared. So on a self-dual background, the anti-self-dual part of F is 0. But if we add one anti-self-dual gluon, then F minus won't be 0. It'll be some tiny amount corresponding to the anti-self-dual gluon we added on top. Right, so you see, so if we want to compute the action and different, two of these epsilons will be the anti-self-dual gluons. And this is why you need two negative helicity gluons to get a non-trivial amplitude at tree level, because there's one wouldn't cut it, because then you have one epsilon here and then the other one would be 0. But if you have, let's say, epsilon I and epsilon j corresponding to the I and j self-dual gluons, then you'll get a non-zero answer. So, right, so you can use this trick to compute the Park-Taylor formula, and that was done by Selivanov and Rosley in 1998. So it's not the hardest thing ever, although their paper's totally unreadable. In any case, so one would want to ask, okay, what's the analogous form of this action, the sort of self-dual rewriting of Yang-Mills for Einstein gravity? And that's given by this following so-called Hlobansky action. I'm not going to go into too much detail, but here, so here I'm using big A and big A dot to be spin indices. You can go between spin indices, in this so-called spin helicity formalism. You can go in between spin indices and regular spacetime indices using the Pauli spin matrices. And here RAB, this is the anti-self-dual part of the Riemann curvature 2 form. Gamma AB is the anti-self-dual part of the spin connection. These sigmas are so-called these are bases of anti-self-dual 2 forms. And here the thetas are tetrads for the space-time. I'm just writing it down. Anyway, yeah, this action equals the Einstein-Hilbert action, just the regular integral over the curvature scalar. So this actually is literally equal to the curvature scalar. But, so that actually vanishes on shell. So that can't, certainly not all the amplitudes are 0. And it turns out the actual correct action to use is one where you sort of integrate by parts. So instead of having the d here, you put the d here, and that corresponds to adding a certain boundary term, and that's the actual correct action to use. In any case, if we're interested in the MHV scattering problem where we have a self-dual background and two anti-self-dual perturbations, then I'll just say that the action becomes the following thing. So here the sigma sub naught, these are the two forms on a self-dual background, and then these little gammas, these are the perturbations to the anti-self-dual part of the spin connection. So usually this anti-self-dual part of the spin connection, big gamma AB, that's 0 in a self-dual background, just like how F minus was 0 in a self-dual background, but then we make a linear perturbation. And then the nice thing about this action is you don't have to compute how the anti-self-dual gravitons interact with each other. You can just sort of compute one of them, and that'll get you the right thing, just in the same way that F squared is like that. Right, so I'll just say a quick word about, okay, how do you add the anti-self-dual perturbations? So very briefly, I'll say you can decompose the Riemann tensor in these spin indices in the following way with these Newman-Penrose scalars. So this is the anti-self-dual part of the Riemann tensor, psi ABCD. This is the self-dual part. And then on a self-dual background, okay, the anti-self-dual part of the Riemann tensor is 0. But a linear perturbation using the Bianchi identity, you can show satisfies this following equation. Oh, that should say equals 0. So this equation that the anti-self-dual part of the Riemann tensor satisfies is actually just a linear perturbation to the Hlobansky equation. So remarkably is the same as linear perturbation to phi, and therefore you can express it using diagrams. So let's say you had two positive helicity gravitons, and you wanted to add in a single negative helicity graviton, you wanted to solve for psi A, B, C, D, you just add in, it's just all of the diagrams with a third, this third thing added. So here, all these, so it's just all the diagrams with a 3 in them. And that's how you can solve for this. So I'm just saying that, there's a diagrammatic way to solve for anti-self-dual perturbations too. And then you can, once you have psi A, B, C, D, you can then solve for the spin connection using this following equation. Anyway, so long story short, you can compute all these objects using tree diagrams, and then you can take this MHV generating function, this sort of sigma wedge gamma, and there are all these rules for combining the diagrams, the squiggly lines, and so forth. And you've got to put some elbow grease in. And in the end, you can prove the MHV formula. Although actually, what you prove is a new slight generalization of the MHV of the NSVW formula. So the NSVW formula is a sum over trees with only the positive helicity gravitons represented. Here, what you naturally get is trees with actually the 2 negative helicity gravitons are also in the diagram, and there's some extra reference spinors involved. If you take the reference spinors to some particular value, you recover the NSVW formula. Okay, so I have about 15 minutes left. I'm just going to give a very brief example as to where my interest in this actually came from, which was the so-called LW1 plus infinity algebra. So you really also shouldn't do this in the talk, just talk about a totally different thing, but doesn't matter. Okay, so LW1 plus infinity symmetry. This is a sort of symmetry that people knew about in self-dual gravity for a long time, and it's manifests a level of twistor space and has some geometric interpretation as deformations of complex structure twistor space. So, okay, what is the LW1 plus infinity algebra? First, I'll define the W1 plus infinity algebra. So, okay, it's the W1 plus infinity algebra is just a name for something you've all seen before. It's just polynomials in 2 dimensions where the Lie bracket is the Poisson bracket. Okay, that's it. So here we have these generators, which are just polynomials in U and W. These are just 2 variables. Here you have a Poisson bracket, once again, U and W. And you take the Poisson bracket, all right, and these polynomials are parameterized by 2 integers, delta and n bar. You take the commutator, you get the following commutator, and these generators live in the W1 plus infinity algebra. Now you can then loopify any Lie algebra. So by just appending onto the generators an extra integer n, I won't say why it's called a loop. It's not that complicated, but anyway, okay. So elements of the LW1 plus infinity algebra are W's of the W1 plus infinity algebra, we add an extra integer. And then the integer, you just add them together at the end, so. And right, so it's a sort of unfortunate notation I couldn't really help, but there are too many W's here. There's actually 3.5 W's because there's this W, there's this W, the frac W, and then U is half of a W. So it's actually 3.5 W's on the slide. Okay, so what does an LW1 plus infinity transformation do to a self-dual spacetime? Well, it corresponds to adding in a self-dual graviton with a very specific wave function. So if you think of the space of self-dual metrics, phi equals 0, that's the flat metric. You can do an LW1 plus infinity transformation by adding in a particular graviton. And the order in which you add in these gravitons matters. So if you add in graviton 1, then 2, it's different than if you add in 2, then 1. And this commutator, that's the LW1 plus infinity commutator. So sort of for generating question for this investigation was I was just wondering, okay, can I just write down like an explicit formula for I just want to take a space-time and just add LW1 plus infinity transformations to it, like let's just say from the flat metric. And you can do that using this perturbator expansion we've been talking about. But the wave functions you use aren't the plane waves. The wave functions you use are these so-called conformal primary wave functions. So now we're going to define some new wave functions that aren't plane waves, but they're parameterized by an integer delta and then 2 complex numbers z and z bar. So we can, so you can also, as a important piece of background, you can rewrite the Lorentz generators as two SL2s. So here we have L0, L1, L minus 1, L0 bar, L1, and L1, L minus 1. No, L1 bar and L minus 1 bar. These are just the 6 Lorentz generators written in our Lycombe coordinates. They satisfy the two commuting SL2 algebra. And you can use these space-time vector fields to sort of take descendants in Z bar and Z. So a conformal primary mode has sort of a direction on the celestial sphere, given by these two complex stereographic coordinates Z and Z bar. But because the L bar minus 1 and L minus 1, these are differentiation with respect to Z, you can sort of trade the angle on the sphere for just sort of fixing it at the North Pole and taking descendants, and these are descendants in the same sense as like in a conformal field theory. And these are the so-called integer modes. Well, these things at the end are the integer modes, where you sort of take Z bar, put them at 0, and then you, don't worry about this constant out front, that's just for convenience, but the main thing is that you take descendants at the North Pole. And the half descendants, so where you've only, let's say, traded Z bar for N bar, but you've kept the Z, these are just the polynomials of the W1 plus infinity algebra. So I'm saying that the wave functions of these half descendants themselves, these are literally polynomials. And so because they're these polynomials, which are sort of shifted with the Z coordinate, if you take two of these half descendants and put them into the Poisson bracket, what you get is the W infinity algebra, right? So you take two of these gravitons with a very funny wave function. They both have the same Z, but they can have any delta and N bar. You put them in the Poisson bracket, you get the W1 plus infinity algebra. Although on the space of self-two metrics, you'll have the loop algebra, you'll see in a second. But yeah, okay. The point is that if you redefine the seed functions to be these half descendants, then this formula, this tree formula we had from before, still holds. You just have trees, but now each node of the tree is a half descendant instead of a plane wave. So we're going to find the action. So, all right. So once again, because this Polanski scalar phi just gives us the action, if we say how LW1 plus infinity acts on the scalar, we say how it acts on the metric. So the action, so we can just take a metric where we have a bunch of seed functions given by half descendants, where each of these points are just a value of Z, where like the half descendant lives, and we just do a loop integral around it and add in another descendant. And that's what gives us the LW1 plus infinity. So this loop integral here, this is just taking derivatives with respect to Z, right? So if you take a half descendant and take descendants with respect to Z, you get the full descendant. So here we're taking like the full descendant. And using a contour pulling trick that's very familiar from 2D CFT, all you need to get the commutator of this action, if you want to get the commutator of this action, you then surround it by another loop integral. And well, the commutator only depends on the pole, but the pole, if two of the gravitons go to the same point, is given by this Poisson bracket, like located at a single point. And so we already discussed earlier how that was the W1 plus infinity thing. So then this gives us the LW1 plus infinity thing. So in other words, we can see that this perturbator expansion has the commutator of acting on self-dual spacetimes. It's the same thing as the literal algebra LW1 plus infinity. Okay, the last thing I'll mention is just how do a set of well-known diffeomorphisms called BMS transformations reside within this story I've set here. So in Bondi coordinates, which I'll denote with uppercase U, R, Z bar, and Z, there exists a set of vector fields called super translations and super rotations, denoted CF and CY, parameterized by functions on the sphere. So F is a function on Z and Z bar, Y and Y bar are just functions of Z and Z bar alone. And super translations are given by the following formula, super rotations given by the following formula. I don't have to look at this too hard, just to say that they are asymptotic. They're just vector fields where the leading components are given by these functions, f and y. And a diffeomorphism acts on a metric with basically the following formula. And this is a sort of standard formula, but you can think of this perturbation another way. You can think of this as sort of adding in an extra seed function as like sort of this thing here, which doesn't depend on, okay, I've cheated slightly with the notation, don't worry about it. But this seed function doesn't, this thing here, you can think of as a seed function. Like you have a pre-existing metric, then you want to add a part linear in C, and then there's sort of a next order correction necessary to make this still like, let's say satisfy the equation of motion. And then it terminates there. So I'm just saying that this tree formula here, if you have a seed function, which is sort of like a pure diffeomorphism, like this thing, then you're going to add in trees that look like this, which is the diffeomorphism itself. You're going to have one where the diffeomorphism kind of attaches to one of the other pre-existing seed functions. And then it turns out that when the diffeomorphism attaches to two things, this actually evaluates to 0. So it actually turns out that for certain sets of these descendant modes, you literally reproduce the, oh yeah, I actually wrote it there. So, right, so for, let's just say, these sets of modes here and here, you reproduce the action of the lead derivative of two rungs of super translations. It's not all the super translations, but it's two of the rungs. And then for another certain rung, you reproduce all of the anti-holomorphic super rotations. And just to say that that's the story resides within this story as a subcase. But there's actually a lot more diffeomorphisms involved for any delta. So there's actually it's more like 2 infinite squares of towers of diffeomorphisms, which is contained in the story. So yeah, this is all part of a paper which isn't released yet, but will be in the future. Anyway, so yeah, to recap, in this talk we discussed how a perturbator expansion for self-dual gravity, could be used to prove the tree formula for the MHV formula in gravity, and could also be used to study LWM plus infinity transformations. Because the idea is that once you have a sort of simple formula that just says, okay, here is the metric. Okay, once you sort of know what the metric is, you're not very restricted in what you can do. Okay, once you have a formula for the metric, you can start using it to do stuff. Okay, so really we have a formula, we use it to do 2 different things. But one would like, so we use the perturbator formula to study MHV amplitudes, you just study LWM plus infinity. But I mean, a very natural question is, so is there some very strong relationship between LWM plus infinity and MHV amplitudes? So maybe there's some kind of current algebra that would give the graviton MHV amplitude. So such a current algebra was given in Yang-Mills by Nair in 1988. And there's this sort of current algebra, which gave the Park-Taylor formula. And this current algebra is intimately connected to, well, I didn't actually mention the twistor string yet, but the twistor string and MHV vertices. So if you could do this for gravity, that would be very interesting. Okay, that's the end of my talk. Thank you.
Are there any questions for now?
Yes?
Yeah, so my question is probably after your last point, already to the question. So you showed how you can generate these diagrams by expanding some, meaning in case of the, I think you explained it for the gauge theory case, but if you apply this the gravity case, then you'd be generating this expansion that you have for the self-dual gravity by expanding an action for a solution. Yeah. You understand what I'm saying?
Yeah, the amplitude, yeah.
So is there indeed an action that combines sort of the symmetries that you were summarizing here? Write down can be used as a generating function.
For what?
For the self-dual gravity amplitude. Say.
Oh, yeah, there's a bulk
well, there's a bulk action for self-dual gravity.
Yeah, but I'm asking sort of more specifically from the CFD perspective, because in the end,
Yeah, I don't think anyone knows of such a thing.
because in the end, your expressions sort of are neatly summarized in terms of this expansion. At least you had to have infinity. So is there something that one can look at?
Is there a 2D action? I don't,
Is there an
I definitely don't
action
know one. I don't think that,
No, but it's basically, you're asking the question here, basically, is there
Yeah.
a connection that generated current output?
Oh.
Current output?
yeah, no, that would be a very nice paper. That doesn't exist right now. That'd be great.
It seems that your results sort of
Yeah,
should at least give you some hints of what
right. That's,
you don't have to get.
I don't have a guess. No. I just put this out recently. It's a natural follow-up, but that'd be great to actually. So, right. I mean, okay. Even for the near, there's only you could say the action was written down by like what Casali and Boo, just like a few, like there's a difference between. I'm asking something even more basic. Is there a current algebra? And then you got a current algebra. There'd almost certainly be some action involving ghosts and so forth. But I just even something simpler, which is just the. Yeah, because there's two ways to write these perturbators, one with the trees and one where you just keep putting in the sort of OPE inspired recursive formula. So it seems like it's almost there, but it's actually quite complicated. I'll just say that the formula, it's just complicated. I'm not sure. You know, there's kind of this interesting, I haven't written down the formula, but you know, there's just, I didn't actually write down the formula. I just sort of wrote down it's a sum over these trees, but I just say, if you look at this formula, it's unclear like where to start. There's like reference spinners with different things, but it would just take some inspiration if it's possible. It might not be possible. So it's logical. Any other questions? Yes.
So I had trouble understanding the earlier question with the epsilon squared.
Yeah.
If you take specifically, let's say, a collinear limit between two different momenta, when you expect the say epsilon 2 to actually add, and when you square them, you'll get something that's like non-zero, at least classically. And so then,
Right. So if you mean literally the momenta are the same.
yeah,
Yeah, then I guess if you wanted literally the momenta to be the same, you would just have a double derivative on that epsilon. I mean, so I would just do that by first taking the momenta different and then taking out limit. That's how. Yeah. But if you really wanted to do that, you would just take two derivatives with respect to that epsilon. And so that in that special case, that epsilon wouldn't square to zero, but it would like cube to zero or something.
right. So
Or-
how does that,
which is
how do
the
you see that from your
So you could just have two different epsilons and, then later take the limit that the momenta are the same. And then, whether you want to consider those two epsilons to be different or not, it'll operationally become the same thing in the end. But I would just say, you don't have to worry about the two momenta being literally the same. If you understand how it works and they're not the same, you can just take them maybe the same after, and that's fine.
right. But if you want to take some amplitude expression later at the end, you want to consider like collinear limits potentially, and
Yeah.
I won't want to like take that limit.
Yeah, well, yeah, as I said, you could take just a double derivative with respect to one of the A's then to get two particles with this creation. And then that would have like a special epsilon, which doesn't square to zero, but like cubes to zero. And that it would end up, yeah, and that,
It wouldn't change things.
no, it wouldn't change anything. It's just sort, yeah. I'll just sort of claim if you think about it, you'll realize it doesn't change anything. Anyone else have a question?
If there are no more questions, then let's thank Noah again. We can maybe also stop the recording. Was it recording?
Yeah, I think it's still, so
Oh.
maybe there's
So I don't know